Okay, let's dive right into this. Welcome to this explainer, where we're going to be exploring the exact science behind redox reactions. Seriously, if you've ever stared at a massive chemical equation and just felt your eyes completely cross trying to track oxidation and reduction, well, you definitely aren't alone. Today, we're breaking down a perfectly structured method to identify these shifts flawlessly, every single time. So let's decode the science together. To start us off, here's a notoriously tricky trap question. We've got ZnO plus C yielding Zn plus CO. Or, in other words, zinc oxide plus carbon turns into zinc and carbon monoxide. If you were staring at this exact formula on a test right now, could you confidently answer which reactant is oxidized and which is reduced? Go ahead, take a mental guess right now. Let's see if we can navigate this trap perfectly.
Section 1. The full marks formula.
So the crucial point here is structure. You literally only ever need two lines to get this right. First, carbon is oxidized to CO by the addition of oxygen. You can see the carbon physically gains an O in the product, right? Second, zinc oxide is reduced to Zn by the removal of oxygen. It started with an oxygen and then it lost it. That simple oxygen transfer is the whole shebang. It's the entire secret to this reaction, leaving absolutely zero room for errors.
To guarantee you never miss a point, let's break this down into a super simple three-step procedure. Step 1. Always name the starting reactant substance. Step 2. Explicitly state whether it is oxidized or reduced. Don't leave anyone guessing what you mean. And Step 3. Give the specific reason. For these equations, your reason will practically always be the gain or loss of oxygen or hydrogen. Hit these 3 steps and you have built an unassailable answer.
And this basically illustrates exactly how to structure your thoughts moving forward. This universally applicable template is just a simple fill-in-the-blank system. For the action part, you name your starting material, choose oxidized or reduced, and then name the product, like substance X is oxidized to product Y. Then you justify it with the reason, by the gain of oxygen. Map every single redox question onto this exact format, and your brain just automatically organizes the chemistry flawlessly.
Okay, moving to Section 2, decoding the chlorine mix-up.
Let's see how our new template holds up against a much harder example. We've got MnO₂ plus 4HCl yielding MnCl₂ plus Cl2 plus 2H2O. Yeah, with all these chlorine atoms rearranging everywhere across the equation, it's really easy to panic and lose track of the core rule. But don't. Just meticulously track the hydrogen chloride, the HCl on the left side, and follow its elements as they cross the reaction arrow.
Now, what's really interesting here is how it perfectly proves our method works, even when oxygen isn't the only player in the game. First, HCl is oxidized to Cl2, because, remember, the rule is the gain or loss of oxygen or hydrogen. The HCl loses its hydrogen to become Cl2, which makes it the oxidized substance. Meanwhile, the manganese dioxide, MnO₂, is reduced to MnCl₂. It started with oxygen, and it lost it. By just relying on the template, this notoriously tricky mix-up becomes completely manageable.
All right, Section 3. Everyday redox reactions.
You know, it is absolutely vital to realize that these micro-level chemical formulas actually dictate our macro-level world. Redox reactions are happening all around us, every single day, and one of the most visible, destructive results is corrosion. The exact same transfer of oxygen and hydrogen that we just mapped out, it's happening right now to the structural steel of bridges, the bodies of our cars, and even the pipes carrying our drinking water. Which kind of leaves us with a massive question to ponder. We know how to track the oxygen, we know how to track the hydrogen, and we can decode the equations. But how exactly are these silent redox reactions systematically eating away at the entire metal world around us? How does the simple loss and gain of an electron translate into literally billions of dollars in structural decay? Think about that the next time you see a rusty piece of iron. Thank you so much for joining me for this explainer, and keep observing the chemistry happening right in front of your eyes.